Hi, welcome to lecture 9.2 covering sum and difference identities. So in 9.1 we were also talking about using identities and we were verifying them. We worked a lot with the Pythagorean identities, even and odd identities. So we've actually already studied sum and difference formulas for sine, cosine, and tangent. And now we're going to do the same type of thing here and see how we can use them. Okay, so the first thing that we encounter in this particular section is moving through a proof, actually. And if you look at the diagram now, I warped the picture a little bit when I put it onto the screen here, but that is supposed to be a unit circle there. It looks more like a unit oval, but it should be the unit circle. But you can see in the description next to it that it says point P, and let me just get a colored pen here so I can point to, no pun intended, point to what they're talking about here. So point P, that's on the unit circle right there, is at an angle alpha from the positive x-axis with coordinates, and let me not write the coordinates in yellow because you wouldn't be able to see those. So point P is at the coordinates cosine, alpha, sine, alpha. Point Q here is at an angle beta. Actually, let me do Q in a different color. That may make it a little easier to think about. Point Q is at an angle beta from the positive x-axis with coordinates cosine beta, sine beta. So nothing new to us there. Note that the measure of POQ, right here, the measure of POQ is, okay, so we're talking about this measurement right here. If I took angle, the full angle alpha all the way to P, and I subtracted angle beta, I'd end up with that pink alpha minus beta, the POQ angle right there. Then if we label two more points on the circle, A, notice that this angle here is also alpha minus beta, as well as that pink angle. So basically, and let me finish this off to make it a little easier on the eyes here. So basically, if you took the pink angle POQ and rotated it clockwise so that ray, or segment rather, OQ rotated down to the positive x-axis, those triangles are the same triangles. And those angles are the same angles that are the central angles at the origin, are the same angles. It's just been rotated through the circle. So let me stop there and just make sure that you're understanding this diagram. In other words, the angle POQ is equal to the angle AO1. Okay, y'all are both good with that. So what we're going to do is prove that because we're starting with the premise that that those two angles are the same, we're going to show that this distance PQ is equal to this distance AB. Okay, and then we're going to use that angle, or I'm sorry, use those distances to show the cosine difference formula is true. So this is going to be the lengthiest part of the whole lesson, and just bear with me because it's a little bit of well, it's not a little bit, it's a lot of algebra. So you know, in all actuality, it's not 100% necessary that you understand what I'm about to do, but I felt that it was valuable to show you this proof so that we're confident with using these formulas and that they're not just drummed up out of thin air and placed in a math book to make you miserable and have to memorize something else. So we'll prove the cosine difference formula, and then we won't prove the other ones that we're going to use because the same method of proof is used for all the others as well. So the reason we're going with difference is because of this right here, that angle that is equal to the green angle and the pink angle is alpha minus beta. So let's go ahead and start making our way through this. So we're going to start out with the distance from P to Q. Now, all I've done, well, let me actually write the general distance formula for you. And this is from way back before you were even in this class, you learned this formula, that the distance between 2 points, and this is all based off the Pythagorean theorem, is the difference of the x values squared plus the difference of the y values squared. So since PQ, remember, let me go back, the coordinates of P were cosine theta, cosine alpha, sine alpha. And Q, it was cosine beta, sine beta. So those are our points that we're finding the distance between. Wrong way. Okay. So all I've done to start out with is input my x values squared plus my y, the difference between my y values squared, and I took the square root of that. So I just placed those 2 points into the distance formula to find the distance of P to Q. Okay, and just stop me if you get lost, and I can go back. Here comes the algebra. So all we're going to do is start simplifying this. So this is the same thing as the square root of cosine alpha minus cosine beta times cosine alpha minus cosine beta. I can already tell I'm going to need another slide with this. I'm going to have to go ahead. I was going to try to do it all on one slide, but that ain't happening. Plus, and so that's just squaring that thing, sine alpha minus sine beta times sine alpha minus sine beta. So all I've done is written out that I've squared those things up underneath the square root. And now I've got distribution to do. So I've got to distribute here, 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 and here, here, and here. Okay, so this is equal to the square root, the big square root, of, okay, cosine alpha times cosine alpha is cosine squared of alpha. Cosine alpha times negative cosine beta is negative cosine alpha cosine beta. All right, going on the inside, negative cosine beta times cosine alpha is also negative cosine alpha cosine beta. And then negative cosine beta times negative cosine beta is positive cosine squared beta. All right, plus sine alpha times sine alpha is sine squared alpha. Sine alpha times negative sine beta is negative sine alpha sine beta. Negative sine beta times sine alpha is negative sine alpha sine beta. And negative sine beta times negative sine beta, I'm going to try to squeeze this in, as positive sine squared beta. I made it. There we go. All right, so let's see. I want to rearrange these things. So I'm going to show you with colors what I'm about to put together. I'm going to put my cosine squared alpha and my sine squared alpha together. Well, around near each other, because that's one of my Pythagorean identities. And I've got cosine squared beta and sine squared beta, that when I add those together, I just get 1. I get 1 for each of those, because remember our Pythagorean identity says cosine squared theta plus sine squared theta equals 1. So I'm going to put those together and call them each 1. And then I've got like terms. My screen just went wonky on me. Hang on just a second. Okay, there we are. Okay, then I've got like terms here. I've got a cosine alpha cosine beta term and a cosine alpha cosine beta term there. And I have a sine alpha sine beta and a sine alpha sine beta. And these are understood -1 of each of those. So understood -1 of each of these two. So all I'm going to do is combine my like terms and then rearrange my sine squareds and cosine squares so that I can call them 1. And I'll keep it color coded. Even though it takes a little more time, I think it's helpful to see what goes with what. Okay, so I'm going to put cosine squared alpha plus sine squared alpha together. And then I'm going to put positive cosine squared beta plus sine squared beta together. And now I'm going to combine the like terms. I've got now -2 of these things that are called cosine alpha cosine beta. And I've got -2 of these things that are called sine alpha sine beta. Okay, let me stop where I am and say, is this making sense so far? Okay, Michelle says yes. Ken's got a question. I'm going to get a sip of water while you're typing your question, Ken. It makes it easier to understand. Oh, so far. Oh, okay, good, good. Okay, so now I'm going to turn my Pythagorean identities into 1. So cosine squared alpha plus sine squared alpha, that's just 1. And then I have plus Cosine squared beta times sine, or plus sine squared beta is just 1. And then I have minus 2 cosine alpha cosine beta minus 2 sine alpha sine beta. Okay? And the only other thing that I can really do is add my ones together, and I could factor out that negative 2 from my cosine alpha, cosine beta, sine alpha, sine beta terms, but not necessary. So I'm just going to leave it here as 2 minus 2 cosine alpha, cosine beta, minus 2 sine alpha, sine beta. Okay, so that's what we end up with when we simplify that whole thing. All right, so I'm going to go to a clean page here and do the same thing for the distance from A to B. Because we know they're equal with the way we set up this premise, so when I get an expression for that distance, so note the coordinates of this point are 1, 0, and the coordinates of this point we're going to call cosine of alpha minus beta. Remember we showed that angle was alpha minus beta, sine alpha minus beta. Oops, minus beta. Okay, so those are the coordinates of A, and then the coordinates of B are 1, 0 because it's on that unit circle. Let me give myself a clean page. Okay, so now I'm going to find the distance from A to B here. Show the distance from A to B. So that is the square root of, another big old square root to start with. Okay, so I have my x values, which the x value of my A point was cosine alpha minus beta minus the x coordinate of my B point was just 1 squared plus sine alpha minus beta minus 0 squared. This one's not nearly as nasty as the other one is because we got a 1 and a 0 to work with. Okay. So I'm just going to write it so I can do my distribution. So this is cosine alpha minus beta minus 1 times cosine alpha minus beta minus 1 plus sine alpha minus beta minus 0 times sine alpha minus beta minus 0. So I'm just squaring those things. Now I'm going to come back and do my distribution here, 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 and here, 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 and here. Each to each. Square root of, okay, cosine alpha minus beta times cosine alpha minus beta is cosine squared alpha minus beta. Cosine alpha minus beta times negative 1 is negative cosine alpha minus beta. Negative 1 times cosine alpha minus beta is negative cosine alpha minus beta. And negative 1 times negative 1 is positive 1. The next one's nice because we got some zeros to multiply with. So the sine of the alpha minus beta times 0 is 0. The sine of alpha minus beta times the sine of, oh, I should have done that one first. Let me back up. Sorry, I got ahead of myself. I got so excited about getting to multiply with a 0 that I skipped multiplying my sine alpha minus beta by itself. So that's sine squared alpha minus beta. Now, sine alpha minus beta times 0 is just 0. 0 times sine alpha minus beta is just 0. And 0 times 0 is just 0. Nice. So, yeah, exactly. Finally, something that's not making us go cross-eyed. All right, so here I have cosine squared alpha minus beta, and I have a sine squared alpha minus beta here. And then I have like terms of negative understood 1 cosine alpha minus beta, negative understood 1 cosine alpha minus beta. And then I just have a 1 that gets combined with these zeros, so it just ends up being 1, hanging off by itself there. Okay, so just rearranging things. I'm going to put my Pythagorean theorem stuff first. So cosine squared alpha minus beta plus sine squared alpha minus beta. Okay, remember that's just 1, and I'll do that in the next step. Then I have plus 1, and now I'm going to combine my like terms there in purple. I have negative 2 of these things that are cosine alpha minus beta. All right, one more step with simplifying this thing. The square root. Okay, cosine squared alpha minus beta plus sine squared alpha minus beta is just 1. And then I have a plus 1. And then I have a minus 2 cosine alpha minus beta. So this simplifies completely to square root of 2 minus 2 cosine alpha minus beta. All right, and since we set up the premise that those lengths AB and the length PQ were equal, I can now come back and say, okay, this thing right here, if that's true, then this thing right here has to be equal to this thing right here. So let me take a picture of this. Excuse me. Oops. Here we are. Okay, so there's my first one. Here's my second one. And we've already said that they're equal. This background. They don't slide all over the place when I start writing on them. Okay, so I can put an equal sign between these things. And let's see what happens when we start working with it. All right, so ignore the boxes that I have around them. I've got square root equaling square root. So the first thing I'm going to do is square both sides to get rid of those square roots. Square both sides. So now I've got 2 minus 2 cosine alpha cosine beta minus 2 sine alpha sine beta equals 2 minus 2 cosine alpha minus beta. And I can subtract 2 off of both sides. And that gets rid of those 2 right there. And then I can come back. I've got a -2 factor in all of these, so I can divide out a -2. And I end up getting my cosine difference formula here. Cosine alpha minus beta is equal to cosine alpha cosine beta minus sine alpha sine beta. And sure enough, that is the difference formula for cosine right there. So, like I said, we are not going to prove all of these because we've got 2 for cosine, 2 for sine, and 2 for tangent. So we would be spending all afternoon if all we did was prove these. But it's the same type of proof for all of the other ones. So hopefully you feel confident enough to just use them now without wondering, oh, where the heck did this thing come from? I assure you it was not a bunch of math teachers sitting around a room cackling and wringing their hands trying to figure out ways to make students' lives miserable. We have plenty of other ways to do that. All right, so find the exact value of cosine pi over 3 minus pi over 4. So from my cosine difference formula, I know that the cosine of alpha minus beta is equal to cosine alpha cosine beta, this is what we just showed, plus sine alpha sine beta. So since I've got a difference on the inside here, I can look at pi over 3 as my alpha and pi over 4 as my beta. So the cosine of pi over 3 minus pi over 4 is the same thing as the cosine of pi over 3 times the cosine of pi over 4 plus the sine of pi over 3 times the sine of pi over 4. Let me go grab a quick unit circle picture to bring in for us. I should have included this on this set of note sheets. I have it on your 9.1 note sheet, but didn't include it on this for some strange reason. But easy enough to grab a Google image real quick and plop it down on the page so we can look at it. Big unit circle. Let's tame that down a little bit. And I'm just going to put it up here and let it float for a minute. Okay, so the cosine, remember cosine is our x value. The cosine of pi over 3, if I look at pi over 3, the x value is 1/2. So this is the same thing as 1/2. Cosine of pi over 4 is square root 2 over 2 plus the sine of pi over 3, which is square root 3 over 2 times the sine of pi over 4, square root 2 over 2. Now I've just got nice, neat little calculation or simplification rather to do here. We multiply fractions straight across, so 1 times the square root of 2 is square root 2. 2 times 2 is 4. Square root of 3 times the square root of 2 is square root of 6. 2 times 2 is 4. I have a common denominator, so I can go ahead and combine my numerators over my common denominator. Square root 2 plus square root 6 over 4 is the exact value of cosine pi over 3 minus pi over 4. That's it. Okay. Now, This next one says, find the exact value of the cosine of 105. So I thought to myself, I was like, okay, so we're using sum or difference formulas here, and 105 is not a special angle on my unit circle. So I thought, okay, what special angles can I either add together or subtract to give me 105? And the first thing that I came up with was 60 and 45 degrees. So instead of finding the cosine of 105, I figure, okay, I'll find the cosine of 60 degrees, that's degrees, plus 45 degrees. And at the very top, you can see that my cosine sum formula is cosine alpha, which is 60 degrees, cosine beta, which is 45 degrees, minus sine 60 degrees sine 45 degrees. Okay? So I just go grab those values from my unit circle like I just did on the last one. The cosine of 60 degrees is 1/2. And I'm multiplying that by the cosine of 45, which is square root 2 over 2. Looking pretty familiar, huh? Minus sine of 60 degrees is square root 3 over 2 times sine of 45 degrees, square root 2 over 2. So no big revelation there. We've got square root 2 over 4 minus square root 6 over 4, which gives us square root 2 minus square root 6 over 4 as the exact value for the cosine of 105 degrees. So now with this one, you should start being able to see the value of this. So taking an angle that doesn't show up on your unit circle and figuring out if there's a possibility of adding or subtracting unit circle angles together to get the angle that you're looking for. Hopefully you begin to see the value of this. Okay, so same type of thing here, except now we're working with sine. So let me bring along my unit circle. Oh, actually, I think I can just paste it again. I think it's the last thing I had on my clipboard. Yep. I don't want to cover up our formulas. Okay, so we have the sine of 45 degrees minus 30 degrees, and the sine of 135 minus 120 degrees. Notice, if you subtract 30 from 45, you get 15. If you subtract 120 from 135, you get 15. So the purpose of this exercise here, this example, is to show you it doesn't matter what special angle you use. As long as it's equivalent, you're going to get the same answer no matter what. So for this first one, we have the sine of 45 degrees minus 30 degrees. And that is equal to, okay, so we're using the difference formula right here. So that is sine of alpha, which in this case is 45 degrees, times cosine of beta, which is 30 degrees, minus cosine alpha, which is 45 degrees, sine beta, which is 30 degrees. Now we just need to go grab our values. The sine of 45 degrees is square root 2 over 2. The cosine of 30 degrees is square root 3 over 2. Minus the cosine of 45 degrees, square root 2 over 2. The sine of 30 degrees is 1/2. So we have square root 6 over 4 minus square root 2 over 4. So my exact value there is square root 6 minus square root 2 over 4. Now let's look at it with the same value once subtracted, but different special angles. Sine of 135 degrees minus 120 degrees. Okay, so that's the sine of 135, which is positive square root 2 over 2. Oh, I'm sorry, I need to just write the degrees first. Sine of 135 degrees times the cosine of 120 degrees minus the cosine of 135 degrees times the sine of 120 degrees. Okay, the sine of 135 degrees is positive square root 2 over 2. The cosine of 120 degrees is negative 1/2. And that's subtracted by the cosine of 135 degrees is negative square root 2 over 2. And the sine of 120 degrees is square root 3 over 2. Okay, so this is negative square root 2 over 4. Now I've got a negative times a negative, so this is plus square root 6 over 4, which leaves me with negative square root 2 plus square root 6 over 4, which is the exact same thing as square root 6 minus square root 2 over 4. Notice we got the same thing, even though they were different angles, because their difference was the same, we ended up with the same result there. All right. Okay, so find the exact value of sine of arc cosine. Remember, we've already studied those sine and cosine inverses. So arc cosine of 1/2, arc sine of 3/5. Hang on, I just lost my daylight. I didn't have a light on in here, and the sun went behind a cloud, so I need to turn on the light. I can barely see what's going on. Okay. So just a quick jog your memory here, and that is that if the arc cosine of 1/2, if we have the arc cosine of 1/2, that means that the cosine of alpha had to equal 1/2. Because remember, that's what arc cosine does, is it says, okay, well, if I start with this right here, and I take the arc cosine, that's going to give me alpha. So because of this, I know that. And because of this, I know that the sine of beta is equal to 3/5. All right. So I start out with the sine of the arc cosine of 1/2 plus the sine, the arc cosine of 3/5, And that, I'm going to set that equal to the sine of alpha plus beta. So I'm going to call that alpha and call that beta, or call the arc cosine of 1/2 alpha and the arc cosine of 3/5 beta. So using my formula, sine alpha cosine beta plus cosine alpha sine beta. And I got that from right here. So the sine of alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta. So that's all I have written right there is my formula that I'm going to use. Well, I know that the sine of alpha is 3/5. The cosine of beta, I don't have yet. Plus, well, I know the cosine of alpha is 1/2, but I don't know what the sine, I'm sorry, sine, I don't know the sine of alpha. I know the sine of beta. Let me move this. The sine of beta is 3/5. So I know cosine alpha and sine beta, but I am missing the sine of alpha and the cosine of beta. So off to the side, let me get a different color and give myself a little room to work down here. The sine of alpha, the sine of alpha has to be equal to the square root. This is just using the Pythagorean theorem. 1 minus cosine squared alpha. Okay? So I know what the cosine of alpha is. I'm trying to figure out what the sine of alpha is. So sine of alpha equal to square root of 1 minus, okay, the cosine of alpha is 1/2. So 1/2 squared, which is equal to the square root of 1 minus 1/4, which is the square root of 3/4, which is the square root of 3/2. And the cosine of beta equal to the square root of 1 minus sine squared beta, which I already know the sine of beta. So that's 1 minus 3/5 squared, which is the square root of 1 minus 9/25. And my 1 is the same thing as 25/25. I don't have room to show my fractional math there, but that 1, when I get the common denominator, is 25/25. So 25 minus 9 is 16/25. So I can take the square root of the numerator, square root of the denominator, and that gives me 4/5. So now I have expressions for sine alpha, square root 3/2, times cosine beta, 4/5. All right, now I'm ready to just do the math. Okay, this is 4 square root 3/10 plus 3/10, which gives me 4 square root 3 plus 3/10. Did I lose y'all in any of that, or are y'all good? Awesome. Moving on to tangents. The tangents look a little nastier in their formulas, but they're really not too bad. Oh, and just as a reminder, tangent theta is equal to sine theta over cosine theta. And cotangent is the reciprocal of that, so cotangent theta is equal to cosine theta over sine theta. Those are our quotient identities. Okay, find the exact value of the tangent of 2 pi over 3 plus pi over 4. So we're going to use our tangent sum formula there. So the tangent of 2 pi over 3, there's our alpha, plus pi over 4, there's our beta, has to equal, and I'm choosing this formula right here, tangent of 2 pi over 3 plus the tangent of pi over 4 and that's divided by 1 minus the tangent of 2 pi over 3 times the tangent of pi over 4. All right. So off to the side here, we'll do the fractiony math to get those tangents since they are a ratio of the sine and the cosine. The tangent of 2 pi over 3, let me paste our unit circle here again, so that you see I'm not just making up these values. Okay, so tangent is equal to sine over cosine. So that's the y value over the x value. And 2 pi over 3, that gives me square root 3 over 2 divided by negative 1/2. Well, I never divide fractions. I multiply by the reciprocal, so that's square root 3 over 2 times negative 2 over 1. My 2's divide out, so I end up there with, oh goodness, when I did it earlier, I didn't carry my negative sign with me. So that is negative square root 3. I put square root 3 down. All right, the tangent of pi over 4 is equal to, okay, so the sine of pi over 4 is square root 2 over 2. And so is the cosine, square root 2 over 2. So that's just 1. All right, let me move my unit circle out of the way and we'll put these values in. I can probably just delete it now. All right. So this is equal to, okay, the tangent of 2 pi over 3 is negative square root 3. Plus the tangent of pi over 4, which is 1, divided by 1 minus the tangent of 2 pi over 3 is negative square root 3 times the tangent of pi over 4, which is 1. Simple enough. I'm going to flip-flop my terms in the numerator because I don't like them to be, I don't like to have that negative leading like that. 1 minus the square root of 3 divided by, in the denominator I have 1 plus the square root of 3. So I have a negative times a negative down there. And that's it. You could rationalize that denominator if you really wanted to go to that trouble, but I believe WebAssign will take that answer for that particular one. Okay, so practice, practice, practice here. Okay, so we've got we are given the cosine, the sine of alpha as 3/5. And we are given the cosine of beta as -5/13. So since we're told what the entire sine is, we need to figure out what alpha and, we need to figure out what the missing values are with our, let me see how I want to explain this. Sorry, I just lost my words. Oh, okay. Because we have tangent down at the bottom of alpha and beta, and in our formulas, let me just go ahead and write the formulas out next to each of these so we have them to look at. Sine of alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta. So, and I'll do the other three in just a moment. So what I was about to say is we know what the sine of alpha is, but we don't know what the cosine of alpha is. We know what the cosine of beta is, but we don't know what the sine of beta is. So we've got to use the Pythagorean theorem in a right triangle to get the other one that we don't have. Let me go ahead and just finish off these formulas here. So this is cosine alpha, cosine beta, minus sine alpha sine beta. Tangent of alpha plus beta is tangent alpha plus tangent beta divided by 1 minus tangent alpha tangent beta. And then this last one, tangent of alpha minus beta, is tangent alpha minus tangent beta divided by 1 plus tangent alpha tangent beta. Okay, so what I was rambling about and probably not making much sense about earlier is what we're about to do now. So since I know, let me get my pink pen here so we can keep this color coded. I know that the sine of alpha is 3/5. Remember way back when we first started all this trig stuff, we figured out that the sine in regards to a right triangle is the opposite over the hypotenuse. So if I draw a little triangle here, and I consider that this is angle alpha, the sine being 3/5 tells me that this side is 3 and this side is 5. And when I put that into my Pythagorean theorem, I have x squared plus 3 squared had to equal 5 squared. So x squared plus 9 equals 25. Subtract 9 from both sides, and x squared is 16. So x is 4. Taking the square root of both sides. I don't have to take into consideration -4 because we're talking about a distance here, and there's no such thing as negative distance. So, and if you consider this point right here to be the center of the circle, then that is a positive x distance there. And we're given the restriction that alpha lies between 0 and pi over 2, so that's between 0 degrees and 90 degrees. on our circle. So that triangle lives in the first quadrant. Okay, let's do the same thing for, okay, so the cosine of alpha is adjacent over hypotenuse, so the cosine of alpha has to equal 4/5 here. Are y'all with me on this so far? And Michelle is? Ken, are you with us? Oh, Ken's got, okay. I saw you had a little bit of a delay on your microphone, so I'm probably going to sound like a chipmunk here for a little bit because it's going to try to catch up. Okay, so now let's work with beta. Uh-oh, Ken just got kicked out. Okay, so cosine beta is equal to -5/13. And we're told that beta lives between pi and 3 pi over 2. So that's between 180 and 270 degrees. So we're talking about this triangle in that third quadrant. Yeah. I was thinking about it, sorry. The cosine of beta is the adjacent over the hypotenuse, so this has got to be beta. This is -5 here because I had to move 5 in the negative direction to get there, and then my hypotenuse is 13. So I have -5 squared plus y squared equal to 13 squared. That's 25 plus y squared equal to 169. Subtract 25 from both sides. So y squared is equal to 144. Take the square root of both. Y is equal to 12. But it is actually -12 because we had to go down to get there. And the reason, the way I knew that is because I was given the restrictions that beta lives between pi, which is 180 degrees, and 3 pi over 2, which is 270 degrees. So I knew that triangle had to live in the third quadrant there. Okay, so since we know cosine of beta is adjacent over hypotenuse, the sine of beta is opposite -12 over hypotenuse, 13. So -12/13. So now we have all the value. Well, let's go ahead and do the tangent while we're doing this side work, because we have to do the ratios to find the tangent. So tangent of alpha equal to sine alpha, which is 3/5, divided by cosine alpha, which is 4/5. I never divide fractions. I multiply by the reciprocal. 3/5 times 5/4. My 5's divide out, and I get 3/4. So tangent alpha is 3/4. Tangent beta, okay, it's sine beta, -12/13. Welcome back, Ken. Divided by cosine beta, which is -5/13. I never divide fractions. I multiply by the reciprocal, so this is -12/13 times the reciprocal, -13/5. My 13's divide out. Negative times a negative is a positive, so I get that the tangent of beta is equal to 12/5. Okay? So now I have all my background work done. Now I'm actually ready to plug these things into the sum and difference formulas. I don't know if I'm going to have enough room on this screen either to do all of them. Okay, so let's start with sine alpha plus beta. So sine alpha plus beta is equal to sine alpha cosine beta plus cosine alpha sine beta. Sine alpha is 3/5. Cosine beta is -5/13. Cosine alpha is 4/5. Sine beta is -12/13. Now it's just a matter of doing fraction-y math. So I multiply fractions straight across. This is -15/65 minus 48/65, and that gives me -63/65. Okay, there's sine of alpha plus beta. Now let's do cosine alpha plus beta. Okay, so that formula is cosine alpha cosine beta minus sine alpha sine beta. Okay, cosine alpha is 4/5. Cosine beta is -5/13 minus sine alpha, that's 3/5, times sine beta, which is -12/13. Okay, so here we have -20/65. And here we have +36/65. Common denominator, so I can combine my numerators over my common denominator, and I get 16/65 for cosine alpha plus beta. Tangent. I might have enough room. Make sure I leave room for the other tangent there. I think I might have enough room. Okay, so tangent alpha minus beta, plus beta is the next one that we had, plus beta is equal to tangent alpha plus tangent beta divided by 1 minus tangent alpha tangent beta. Okay, so the tangent of alpha is 3/4 plus the tangent of beta is 12/5, and that's divided by 1 minus 3/4 times 12/5. Well, to add those fractions in my numerator, I have to have a common denominator. So I'm going to come back and multiply by my clever form of 1 with both of those fractions. This one needs to be multiplied by a 5/5, and this one by a 4/4. And I'm going to go ahead and multiply this one by a 20/20, because when I multiply 4 by 5 in that other denominator that I'm going to combine with, it's going to be 20. So hopefully that didn't confuse you there. Okay, so this is 15/20 plus 48/20 divided by 20/20, that's 1, minus 36/20, which is the same thing as, okay, so now I'm ready to combine my numerators over my common denominator. 15 plus 48 is 63. So this is 63/20 divided by 20 minus 36 is negative 16/20. And I never divide fractions. I multiply by the reciprocal. So 63/20 times the reciprocal negative 20/16. My 20s divide out, and I end up with negative 63/16 there. And that does not reduce. The factors of 63 are 3, 7, 9, and there's some higher up, but we don't need to go higher than 16. And 16 is even, so it's 2, 4, 8, 16. So that's as far as you can go with that. Okay, the tangent of alpha minus beta is equal to tangent alpha minus tangent beta divided by 1 plus tangent alpha tangent beta. It's just our formula there. Okay, so let's plug our values in. Tangent alpha is 3/4. And I'm subtracting tangent beta 12/5. So it's going to be the same getting the common denominator as it was in the last one, but I'm subtracting them. That's the only difference. And down here I'm adding 1 plus tangent alpha 3/4, tangent beta 12/5. So I'm not going to show how I got the common denominators. I'm just going to say this is the same thing as 15/20 minus 48/20 divided by 20/20 plus 36/20. Okay, so 15 minus 48 is negative 33. So I've got negative 33/20 divided by 56/20. I never divide fractions. I multiply by the reciprocal. Negative 33/20 times 20, 56. My 20s divide out, and I have negative 33/56. Woo! That's it for that one. I'm sorry, did y'all have any questions about that one? Hopefully you asked them as they came up, because that one took a while. That one took almost as long as the proof at the first. Y'all good? Great. Okay, so cofunctions. So we have our right triangle set up over here, and we know that this is 90 degrees. And 90 degrees is the equivalent of pi over 2 radians. So if I call this right here angle theta, I know that the other two angles put together make 90 degrees, so I know that this other angle has to be equal to pi over 2 minus theta. So that's just setting up that relationship of that right triangle there. And what we get from this is our cofunction identities. I will show one of them down at the bottom, and then we'll just accept the other ones. So we can verify all of these cofunction identities by our difference formulas. So that's what I'm going to do for that first one. I'm going to start with the difference, the cosine of pi over 2 minus theta, and show that that's equal to sine theta. So I start out with cosine of alpha minus beta. That formula is cosine alpha, cosine beta. By the way, I am going to allow you to have a formula sheet on the final exam, so don't freak out with all these formulas that you have to remember. Sine, yeah. I kind of look at formulas as stuff for books to hold. So, I mean, it's nice if you have them memorized, but with our Google society that we have today, it's nothing that you can't find exactly when you need it. So, all right, so cosine of pi over 2 minus theta. We'll set it up using our cosine difference. Yes, there is a lot of them. We'll set it up using our cosine difference formula here. So this is the same thing as cosine of pi over 2 times cosine theta plus sine pi over 2 times sine theta. Let me see if I still have my unit circle. Can't remember if I've done something since then. Hey, there it is. Just stick it there. Make it a little bit smaller. We only need the pi over 2 angle, which is 90 degrees right there. Let me tell my husband no. Okay. All right. So you can see the coordinates for pi over 2 are 0 and 1. The cosine is 0, the sine is 1, so that makes this really nice, neat, and quick, believe it or not. After everything we've been through, this is easy. Cosine of pi over 2, that's the x value, so I've got 0 times cosine theta plus sine of pi over 2 is 1 times the sine of theta. That is 0 plus sine theta, and we have just shown that the cosine of pi over 2 minus theta is the same exact thing as the sine of theta. That's it. And we're not going to do it for the other ones. I just wanted to show you one of them. Write the tangent in terms of its cofunction. So they just want us to apply the cofunction identity here. So the cofunction of tangent, I'll write it at the top. Tangent theta is equal to cotangent pi over 2 minus theta. Okay? So the tangent of pi over 9 is the same exact thing as the cotangent of pi over 2 minus pi over 9. I need to get a common denominator there to be able to combine those fractions. So I'm going to multiply by 1 in the form of 9 over 9 there, and multiply by 1 in the form of 2 over 2 here to get 18 in my denominator. So that's the same thing as the cotangent of 9 pi over 18 minus 2 pi over 18. Now I'm ready to combine my numerators over my common denominator. This is the same thing as the cotangent of 7 pi over 18. That's it. They just wanted us to write it in terms of its cofunction. Okay? Write the sine of pi over 7 in terms of its cofunction. So the sine of pi is equal to the cosine of pi over 2 minus beta. So the sine of pi over 7 is equal to the cosine of pi over 2 minus pi over 7. We need to get a common denominator again. So I'm going to multiply this one by 7 over 7 and this one by 2 over 2. And that leaves me with cosine of 7 pi over 14 minus 2 pi over 14. So this is the same thing as the cosine of 5 pi over 14. Whew! All right, using sum and difference formulas to verify identity. So this is going to start feeling like what we did in 9.1. Okay, so we have the sine of alpha plus beta plus the sine of alpha minus beta, and we're going to try to show that some way all of that business is equal to 2 times the sine of alpha times the cosine of beta. So we're going to use our sine, sum, and difference formulas and apply them to alpha and beta to see that it comes out as 2 sine alpha cosine beta. So the first one is the sum formula. I'm going to put these in brackets here. I should probably color code these. Let me do that. We'll do the sum in purple here. Okay, so this is sine alpha cosine beta plus cosine alpha sine beta. And I'm wanting to add sine alpha minus beta. So this is sine alpha cosine beta minus cosine alpha sine beta. Okay? So I'll just point out that there's an understood 1 in front of these sets of parentheses that get distributed, so the parentheses can just fall off. I used the parentheses just to hold those expressions together so that you could see where they were coming from. Okay, so really what I have is sine alpha cosine beta plus cosine alpha sine beta plus sine alpha cosine beta minus cosine alpha sine beta. All right, notice that I have positive cosine alpha sine beta, negative cosine alpha sine beta. So those are opposites. They make 0 when combined. And what I'm left with are like terms. I have a sine alpha cosine beta, understood 1 of those, and understood 1 sine alpha cosine beta. So I end up with 2 of those things called sine alpha cosine beta, which is exactly what we wanted to show there. Verified. Yay. Let's move forward unless you have a question. Okay, verify the following. We start out with sine alpha minus beta divided by cosine alpha cosine beta. So I will put the formula for the sign difference formula there in purple. Okay, so sine alpha minus beta is the same thing as sine alpha cosine beta minus cosine alpha sine beta. And that is divided by cosine alpha cosine beta. Okay, so I'm just going to use my algebra skills to see that if I can make this look like tangent alpha minus tangent beta. Well, I see that I need to end up with two terms. And what I'm basically looking at here is two fractions that happen to have a common denominator of cosine alpha cosine beta. I'm going to split those fractions back up. So this is the same thing as sine alpha cosine beta over cosine alpha cosine beta minus cosine alpha sine beta divided by cosine alpha cosine beta. And now I've got some common factors that I can divide out. I've got cosine beta divided by cosine beta and cosine alpha divided by cosine alpha. Don't forget that the tangent is equal to the sine over the cosine. So here I have sine alpha divided by cosine alpha minus sine beta divided by cosine beta. That's the equivalent of tangent alpha minus tangent beta. We're done. Verified. Okay. Verify that the tangent of pi minus theta is equal to negative tangent theta. So I'm going to use my tangent difference formula there. So the tangent of pi minus theta is equal to tangent pi minus tangent theta divided by 1 plus tangent pi tangent theta. Okay? And let me paste my unit circle here so we can, because we can do the tangent of pi. We know what that is. So pi is that 180-degree angle. Don't forget tangent is sine over cosine, so that's y over x. So in this case, get my pen back. The tangent of pi is 0 over -1, or 0 divided by -1, minus tangent theta, divided by 1 plus tangent pi, once again, 0 divided by -1, tangent theta. So that's times tangent theta, which is the same thing as 0 minus tangent theta divided by 1 plus, well, 0 times the tangent of theta is just 0. So this is negative tangent theta divided by 1, which is just negative tangent theta. That's it. We've got 2 more problems. I appreciate y'all hanging in there with me. Nope, we've got 1 more problem. Yay. Oh, and it's a doozy. Of course. We got to end up with a doozy here. Okay, so for a climbing wall, a guy wire R, so that's that top orange line, is attached 47 feet high on a vertical pole. added support is provided by another guy wire S, attached 40 feet above the ground on the same pole. If the wires are attached to the ground 50 feet from the pole, find the angle between the wires. Okay, so we are looking to find angle alpha there. Here's what we know. I'm just going to color code my little diagram here. I have angle beta, which is this entire angle here. And I'm looking for angle alpha, this little baby angle right in there. That's alpha. So if I could figure out angle theta right in here, then I could subtract theta from beta and get alpha. Let me stop and say, did that make sense, what I just said? Okay, Ken says yes, Michelle. Okay, good. I started to confuse myself there for a moment, so I wanted to make sure I was making sense to somebody in the room. Okay, so just as a reminder, tangent theta is going to be equal to the opposite over the adjacent. I'll just point out we've got a 90-degree angle here. The reason I'm using tangent is because I don't have the hypotenuse for either of those triangles. But I've got the opposite and I have the adjacent for both of those triangles. So I'm going to be working with tangent here. So the tangent of theta has to equal 40 over 50. That's my opposite over my adjacent, which reduces to 4/5. And that theta, don't forget, the tangent of theta is also equal to the tangent of beta minus alpha. Remember, we established that at the beginning. Let's go ahead and do the tangent of beta. The tangent of beta is equal to opposite over adjacent, so that's 47/50. All right, here we go. Let me give myself some room to work here, just in case I need that top part too. All right, so we've got the tangent of beta, and we have the tangent of beta minus alpha, which is theta. So if we do the tangent of beta minus alpha, we get tangent beta minus tangent alpha divided by 1 plus tangent beta tangent alpha. Okay, we know what the tangent of beta minus alpha is. That's equal to 4/5 right here. Tangent of beta minus alpha is equal to the tangent of theta, which is 4/5. So I can put in 4/5 here. Starting to look a little easier on the eye. I also know what the tangent of beta is. It's 47/50. So I can plug that in here and here. And all I'll be left with is solving for the tangent of alpha. So if I can solve for the tangent of alpha, then I can take the arc tangent and figure out what alpha is. Okay, so 47/50 minus the tangent of alpha divided by 1 plus 47/50 times tangent alpha. Okay. So I have well, I should probably combine like terms first. I mean, add my fractions, yeah. I'll do all the nasty work first. Okay, so to be able to combine the fractions in the numerator and the denominator, on the right-hand side, I've got to have a common denominator. So I need to multiply this negative tangent alpha by 50/50 to get that 50 in the denominator. And this fraction in the denominator is 47 tangent theta over 5. So I need to, oh, no, it's over 50. I just didn't write the 0. Divided by 50. Sorry. So I need to multiply that 1 by 50/50 so that I can combine those as well. Okay, let me clean this up a little bit. So we have 4/5 is equal to 47/50 minus, this is 50 tangent alpha over 50. Big divided by 50/50 minus 50 tangent alpha. No, I'm sorry, 47 tangent alpha. I went cross-eyed there for a second. Was looking in the numerator. Sorry. 47 tangent alpha over 50. Okay, still not completely cleaned up yet. So 4/5 equal to, I can combine my numerators over my common denominator now. So this is 47 minus 50 tangent alpha divided by 50, big divided by 50 minus 47 tangent alpha divided by 50. And on the right-hand side, I never divide fractions. I multiply by the reciprocal. So 4/5 is equal to my numerator fraction, 47 minus 50 tangent alpha divided by 50 times my reciprocal 50 divided by 50 minus 47 tangent alpha. Woo! We will come all the way up to the top to continue. So I have room to finish. Okay, so my 50s divide out down there. At least I don't have to worry about those anymore. And what I end up with is 4/5 equals 47 minus 50 tangent alpha divided by 50 minus 47 tangent alpha. Now that I have a proportion set up, which a proportion is just calling two fractions or two ratios equal, I can do what we call cross multiply. Now I hate to use that language because it usually confuses students and makes them think that they can just multiply diagonally wherever they are, but I'll say this. Cross multiplication only happens across an equal sign. Cross multiplication only happens across an equal sign. So please don't use it willy-nilly. Only use it when you have a proportion set up. So 4 times 50 minus 47 tangent alpha is equal to 5 times 47 minus 50 tangent alpha. Now I've got distribution. 4 times 50, 4 times negative 47 tangent alpha. 5 times 47, 5 times negative 50 tangent alpha. And I get 200 minus 188 tangent alpha equals 235 minus 250 tangent alpha. So I need to get my tangent terms on one side and my constants on the other. So here I am going to subtract 200 from both sides, and I'll add 250 tangent alpha to both sides. So those 200s make a zero pair, and this negative 250 tangent alpha and positive 250 tangent alpha make a zero pair. So now I have positive 250 tangent alpha and negative 188. I'm sorry, not negative 180. Is it negative? Uh-oh. I didn't have it as negative. It should be positive. Where have I messed up? Hang on just a second, because I checked my answer and I know I was right when I did it earlier. This be plus. Oh, that was supposed to be plus. Really? Oh, here's where, okay, I'm going to do this in green so you can see where no, I'll do it in orange since it's not on the board yet. Notice this is a plus right here. This is a plus. I lost the plus there, which loses my plus here, my plus here. I'm so sorry, my plus here. Whew, my plus here. And my plus here. Okay. Oh, I'm glad I found that. I'm glad I worked the problem out before I did the lecture. Okay, so 188 tangent alpha plus 250 tangent alpha gives me 438 tangent alpha. And that is equal to 235 minus 200, which is positive 35. All right. I'm going to divide both sides by 438. When I was in graduate school, I was renowned for losing a negative way back at the first of the problem. And my study partner would be like, Libby, you just did 2 pages worth of a problem and you lost a negative right in the second step. So frustrating. 35 over 438. Okay, so we have a value for tangent. So the tangent of alpha is equal to 35/438. So what we can do is put the arc tangent of 35 over 438 into our calculator, and that's going to give us alpha. And when I put that into my calculator, I get that it's approximately 0.0797392416. So that is alpha. So alpha is approximately that long, nasty number, 0.07973924416. But we need to get it in degrees because that's how we were, that's how we'd like to talk about an angle of a guy wire there. So I'm going to multiply it by 180 over pi, going back to the very beginning of the semester, and we get that this is approximately 4.57 degrees. So that little angle between guy wire R and guy wire S is approximately 4.57 degrees. That's all I have for you for 9.2. I hope that was helpful.